Hello, in this video, we're going to cover triple integrals. So to start, we're going to start off with the triple integral problem. So what is the triple integral problem? So the idea is that you have a three-dimensional system. Every point in 3 dimensions is assigned a value. And that value is going to be f of x, y, z. Okay, so we have a function that for any point in R3, you can take the coordinate and plug it into the function, and it will produce a value. In addition, we're going to suppose that we have a region. So we've got a region B that is in R3. So we're going to just sketch a generic region. There's going to be a method to this. So this is the base of the region that's directly beneath it. And then above the region, we are going to have two surfaces that are going to allow us to bracket in a space, a region in space. So this, we'll say this is the top region. And then we need a second one. Let's try and draw it over here. Okay, and so we'll say that we need to define these. So we'll say this guy is g1 of x is this curve here, and we'll say that this curve on this side is g2 of x, and then these surfaces are defined by h2 of xy. That's the top one, and the bottom one will be h1 of xy. Okay, and then so if you start at the base here that's directly beneath the surfaces, and you just extend it upward, it's going to create our three-dimensional object. So if we go up, it's going to eventually hit the bottom surface. We'll say it hits there, then the top surface, and we can go up, hits the bottom, the top, and we can go up from here. It's the bottom. Say there for the top, and from here we'll go up. It's the bottom and the top. All right, and then on the surface here we can draw in some curved lines to represent the fact that we've got our surface here. And we end up with an object, right? A region. So this is our region B. So the problem is, the base problem for triple integrals is what we want to do is we want to figure out if we took all the values that we would get by taking points and plugging them into f of x, y, z, all the values that are inside of this region, and we added them all up, what would we get? What is that? What is that result? So what is the sum of f of x, y, Z inside B. Okay, so to try and give maybe an example that you could wrap your head around. So the example that I usually use is to think of f of x, y, z, to think of it as temperature. So you can use anything that you could define in 3 dimensions as your example. The one that I like is temperature because I think it's the easiest to wrap your head around. So temperatures in 3 dimension are not consistent, like in a room, for example. So temperatures near lights, lights give off heat. So temperatures are going to be higher near lights. Temperatures are going to be higher near bodies because bodies give off heat. And so if you were to go through and look at a room, every point inside of a room would have its own unique temperature. And then we could go through and pick a part of the room and say, what if we were going to go through and add up all of the temperature that's inside of this part of the room? You might think, oh, why would you do that? That would be completely useless. Well, if you did go through and add up all of the temperature inside a part of the room, and then you went through and you found the volume for that temperature, for the volume for that part of the room, you could divide the two to get the average temperature inside of that part of the room, right? Does that make sense? So if you went through and added up all the temperature inside of a bubble, and then you divided by the volume of the bubble, then you could find the average temperature inside the bubble. And so, examples like that, there are uses for going through and trying to find the sum of something, a temperature that's inside of a bubble. So how do we do that? All right, so let's see, how could we go through and do that? What we're going to start off with is going through and figuring out, how do we add up temperature? How do we add up f of x, y, z? And the way that we're going to do that is we're going to start off with a cube. All right, so we're going to suppose that we've got a cube. This cube is in 3 dimensions. Okay, and then the idea is that if we've got this cube and it's in 3 dimensions, then somewhere inside of this cube, we could go through and we could find the value of f of x, y. So we're just going to pick a spot. It doesn't matter where this spot is. We're going to say we're going to pick that spot there, and we're going to say we can go through and find f of x, y, z in that spot. Okay, if we go through and find the volume of this box, so the volume of the box, we could go through and define, let's say that the length of this side is change in x. The length of this side here is change in y. And then the length of this is change in z. Then the volume of the box would equal change in x times change in y times change in z. And then we know that somewhere inside that box, we have a temperature. Say, we check this spot here and we have 75 degrees worth of temperature there. We're talking about Fahrenheit here. So say we've got 75 Fahrenheit in that spot. So what we could do to figure out how much total Fahrenheit is inside that box is take the volume of the box. Okay, that's the amount of space there is, and then multiply it by a single value inside that box, and that would give us, single temperature, and that would give us the amount of temperature that's representative of that box, right? So the amount of f of x, y, z inside the box is f of x, y, z times change in x times change in y times change in z. Okay, so if we've got the box, we know how much total space there is, how much total size the box has by looking at the volume. And then if we've got a point inside there, we can go through and find the amount of temperature, or the amount of f of x, y, z inside the box by taking volume times a representative point. And so before we move much further here, I do want to comment on, so if you're sitting there, wait, what about that? Why is that? What about that point? Why does that matter? Well, if you go back to previous examples where we have ended up using integration, we've always used a representative point inside of, as part of going through and finding a sum of something. So if you go back to single integrals, the first integral example you might have learned is use the left side of the height of the rectangles, and then later you used, I could use the right side as the height of the rectangles, and I would have gotten the same result. Or you could use the midpoint as the height of the rectangles, and you would have gotten the same result. No matter what point you pick inside the interval for each rectangle in a single integral, you end up getting the same result as you take the number of rectangles and have them go to infinity. And so we're doing the same thing here. We're just picking a representative spot. And what we're going to do is we're going to take the number of these cubes and we're going to have them go to infinity. So they're going to shrink down really, really small. And so it doesn't really matter what specific spot we pick, just as long as it's somewhere inside of the box, inside of the cube. Okay, so what we've done is we've gone through and we've found a way to count up volume for one for a cube. So the next thing that we need to do is we need to take the cube then, and we need to fill this space with cubes, right? If we could find the amount of f of x, y in a single cube, then if this entire space was filled with cubes, we could go through and we could add up the f of x, y in each cube and end up getting the total sum of f of x, y inside B, inside the region. Okay, and so that becomes our next goal, is to move on from this idea of the cube and instead focus on how could we go through and fill this entire thing with cubes. Okay, the way that we're going to do that is going to be kind of a natural extension from techniques that we've used, for single integrals and for double integrals. What you're going to do is you're going to just kind of pick a spot inside here. So we can go through and just draw a little cube inside here. Okay, so pretend that's a cube. Okay, I didn't draw it's not the greatest cube, but pretend it's a cube, right? So right there, we've got one piece of this region. We can go through and find the f of x, y in it. And so what we can do next is just take this little cube, and we want to go through and just add it up, move it around, add it up across this entire thing. So the only thing that's really important about it is that you're kind of strategic about it, and you're just kind of consistent for how you handle that. So what we're going to do is you could put a cube on top of that cube, and that would get you the next, get you another piece of the region, and then you could put a cube on top of that cube. And so you could do kind of a vertical stripe, vertical strip, I should say, a vertical strip of cubes, and that would get us the amount of f of x, y, z. That would get us the amount of stuff that's there that's directly above this piece of the base. Okay, that little red box in the base. And then what you could do next, after you've gone through and done that vertical strip, is you could go through and you could do a vertical strip next to it. And I'm going to try and draw a cube, but it's kind of getting off, the picture's getting to be really messy. But there's another strip of cubes directly to the right of the previous one we drew. And then you could go through and do another strip and another strip and another strip. And you could work your way all the way across this object. Oops, looks like I started at B. I should have started at A. But anyway, you get the idea, right? So we start off with a little spot on our base, add up a vertical strip, move over, add up, move over, add up, move over, add up. And you just do that all the way across. And then once you get from one end to the other, you then kind of move over, and then you could do the vertical strip above that square, and then the vertical strip above that one, and then the vertical strip above that one, and above that one, and above that one, and so on. And you could work your way across doing vertical strips each time, and then horizontal strips here across the base. And as long as you're systematic, the way that we've described this, you could go through and you could fill the entire region B with cubes. Okay, so what would that end up looking like as far as kind of trying to tie this in with our previous ideas of integration? So the idea is what we're going to do is we're going to start with these the vertical strip that we're doing here. So we're going to go through and say we have a summation. We're adding up f, x sub I, y sub j, z sub k. Okay, we're going to go ahead and put change in z. I'm going to put change in y, change in x. The order here is going to end up mattering, but it's something that is more important down the road. So one thing at a time. All right, so I'm using different subscripts for each one of these because we're going to have different points to fill in the region. You need three different values to represent all the different locations inside of region B. As far as the thing that's going to vary here, since I'm doing the vertical strip, that's what this thing is, the vertical strip first, only the z sub k is going to be changing here. And the way that we're going to handle that, we're going to do change in z first. Again, this is how you go through and do integrals. You always start off with, what is the change, what's the size, the vertical size for your cubes? What is this value? So you always pick one of those and do that first. And what that's going to be is it's going to be the total length from one side of the other, the total vertical length of the vertical strip here. So to figure that out, what you need is these two things. So we're going to go from h2 of x sub I, y sub j, to h1 of x sub I, y sub j. And then that's the total length of that strip. And then you need to divide it by how many we're going to have. We're going to do for that. I'm going to put that's not a 0, it's an O. So we're going to have O number of cubes, vertical cubes here. And then once you've got that, let's see, do I have room over here? I guess I'll try and squeeze it in. So z sub k is going to be h1 of x sub I, y sub j, plus, okay, so you're starting here at the bottom, and then to go through and figure out where each one of these cubes is going to be located, what we're going to do is we're going to add the change in z times the k value. Like that. So k is what we're incrementing here. We're incrementing from 1 to O. And we're going to, for each one, we're going to start at the bottom one, H1. Oops. Start at the bottom one, H1, and then we're going to add the change in Z amount of distance times the kth cube. So for the first cube, it's going to be H1 plus change in Z. So we're at the top end here for the first cube. This is the location for the first cube. That's H1 plus 1 change in Z. And then if you go all the way to the last one, you'll be at the very top here. Okay, so we're using like the top part of the cube as the location for where we're plugging in f of x, y, z. So now, again, from previous experience, we've seen this before. As long as you go through and do a limit, as long as we take the limit as O goes to infinity, this is going to become an integral. So we're going to have an integral of f x sub I, y sub j, z, dz, and then we're going to leave change in x, change in y, change in x alone for now. And this integral goes from one side to the other. So it's going to go from h1 x sub I, y sub j to h2. It goes from the bottom to the top. And so that is the vertical strip. So the vertical strip is going to be this. This is kind of a, you can even label it. So it's a vertical strip. Okay, so once we have that, that'll get us the exact amount of stuff vertically here. And then the next thing we need to do is we need to take those strips and we need to move them across the base. Okay, this is the part where what we're going to do is we're just going to co-opt our result from double integrals. So double integrals were all about adding up stuff across a base like this. And so, you know, again, we're just going to kind of skip over a lot of the details here. But the idea from double integrals is you start off, you went through and you said, all right, so we've got a double summation. We go from, I equals 1 to n and j equals 1 to m. And we have some function. Instead of using f here, let's use a different letter. We've got f, g, and h taken up here. I don't know, use p. So we got p of x sub I, comma y sub j, change in y, change in x, right? And then we go through and took the limit as m and n went to infinity, right? This was our last result. So, and we said this turns into, double integral p of x comma y dy dx. And then we've got from g1 of x to g2 of x, and then from a to b. So this is, again, co-opting our result for double integrals. So what we're going to do is we're going to take this result, and instead of doing it for p of x, x sub I, y sub j, where p is just a vertical surface that's above the xy plane, which is what we did previously. What we're going to do is instead, we're going to take this thing and we're just going to pop it right into that. So we're going to say, instead of the p representing some surface above our xy plane, we're going to say that the p instead is the vertical strip here. And so what you can do is you can go through and say, I'm just going to substitute in here. All right, so we've got integral h1 x sub I, y sub j. Actually, I'm just going to erase this. H sub 1, x sub I, y sub j. H2, x sub I, y sub j. And then f of x sub I, y sub j, z, dz, change in y, change in x. So I'm just replacing this, replaces p of x, y that I just had a second ago. Okay, and by doing that, notice that p of x, y, it's a function where you plug in x sub I, y sub j, out comes a value. That's what p of x, y, that's what our unknown function p is here. You just plug in an xy coordinate and out comes a number. Well, look at this. This is no different than that. You plug in an x and a y and out comes a number. Okay, it's just very complicated looking function of p of x, y, but you can just substitute and just replace this with it. And by doing so, we can then just inherit the result that we had previously, which is that these two integrals, or these two summations, turn into integrals. And then we keep our inner one here, xy, h2 of xy, f xyz, dz, dy, dx. And then we have g1 of x, g2 of x, and then from a to b. This here, this result, there's our triple integral. And so that's what a triple integral is. It is a sum of function f of x, y, z. So you're adding up f of x, y, z over a region B. And in this case, the region B is all just kind of is what is represented by these things here, by the bounds. Right, and if you look over at our picture, you can see that. Okay, so if we look at our picture goes from H1 as the bottom to H2 as the top, H1 bottom, H2 top, and then G1 and G2 are the left and right side from the base. Okay, so there are a bunch of different important results that come from this. The first thing that you really need to understand about triple integrals is that the way that we've gone through and defined this one, where we have the left side is a curve and the right side is a curve and the bottom is a curve and the top is a curve, is one of 6 possibilities. So there are 6 different ways in which you can go through and define 3-dimensional objects, and each one of those 6 is going to represent a different order of integration. So in this case, we did z first, and then we did y, and then we did x. Okay, so let's just briefly look at some of the others. I'm not going to go over all of them just because it takes a while to look at each one, but let's look at a couple of the others. All right, so let's say case 2. What if our order of integration was dz, dx, dy? Okay, in that case, what type of an object are we talking about? So since z is first, so the first thing kind of gives you the orientation of the surface, ignoring the base. The base comes from these two. So the base is still going to be x and y. It's still going to be on the xy plane, but z tells us that the orientation of the surface is going to be above the xy plane since we're doing z first. So you could kind of start off by drawing, some a vertical surface above the xy plane. And then a second one. And then we can go through and kind of make this look like a surface. Okay. And now directly beneath this, we're going to have our base. And since x is first, okay, what that means is that our surface is going to be oriented relative to, our base is going to be oriented relative to the y-axis, okay, instead of the x-axis. So x is the distance. So the way to think about x is the amount of distance from in the x direction, right? So if we go through and we say x is 2, that means we go 1, 2 units. So we go this way off of the in the x direction. So we're going to have curves that are an amount of x distance. And if we have curves that are an amount of x distance, then that means those curves are oriented this way. This is the amount of x distance, x distance, x distance. Okay, and then the y, if y is last, whatever is last has the flat edge. So we're going to have a flat edge in the y direction. Okay, and so that's the way that you can go through. And so z is above, it's points that are z units. Z goes this way, so you have vertical stuff if you have z first, and x goes this way, so we have stuff that goes, perpendicular to the x. No, perpendicular to the y. Sorry, it's in the x direction is perpendicular to the y, and then last is y. And then from there, to go through and get the actual object, you can go through and just do the same thing we did before. So you start off in this corner, go up until you hit the bottom, then keep going up, go up until you hit the bottom surface, go up until you hit the bottom surface, go up until you hit the bottom surface, and then you can just kind of connect some curves here. Just make it kind of look like it matches the surface. All right, and so we get our object, and so you can see dz, dx, dy would be a surface that has this orientation instead. So second one would be if we have a surface where we have a curved you could think of it like we have a curved front and back and a curved top and bottom, but flat sides. That's as compared to this case where we have a curved left and right, a flat front and back, and a curved top and bottom. Okay, and so there's 6 possibilities. So third one, just to pick, there is no set way to number these, but we could say that we do, I don't know, dx next, then dz, dy, and we'll just call this case 4, would be x, and then y, and then z, and then we'll say case 5 would be y, and then I don't know, z, and then x, and then we'll call case 6. We could have y, then x, and then z. All right, so let's pick one more of these just to illustrate, again, like what the surface would end up looking like. So we'll talk about how to go through and pick which is the right order when you're actually doing a problem. I'm just showing you that there are the different cases, the different situations. Let's do this one. All right, so we're doing x first. So in terms of going through, what does that mean? Well, so when we did z first, it meant that we had surfaces that were above the xy plane, right? They were in the z direction. You went in the z direction to define them. So if we have x first, that means we're going to have surfaces that are oriented relative to the yz plane. You're going to go in the x direction to define them. All right, so let's see if we can successfully draw some surfaces that are oriented relative to the xy plane. And we'll say this is the left side and right side, something like that. And then let's do another one over like here. All right, those look like they're oriented relative to the xy plane, right? Or to the yz plane, right? And then next, what have we got next? So we're looking at z first. So if we have z first, that means our curves that were for our base we're going to go in the z direction. If we're going in the z direction, that means we're going this way. That means that our curves are oriented perpendicular to the y-axis. So let's use a different color. Let's do, how about this? And then that. Okay, and then finally, y is last. So since y is last, you want sharp edges in the y direction. Okay, and then so to go through and draw your object, what you do is from here, you want to go in the x direction until you hit the surfaces. So we'll go in the x direction and we'll say we hit that surface there. And we'll say we hit that surface there. And then here we go in the x direction and we'll say we hit that surface. Let's say there to there, there to there, and there to there. Okay, and then for the, we've got just trying to maybe make this match here. Surface. And then this way. And we get our three-dimensional object. So this object has a curved front, a curved back. Those come from these surfaces. And it has a curved top and a curved bottom, but it has a flat right side and a flat left side. Okay, so in this case, this would be H2. And now what variables do we want? We want the variables that are affiliated with the base. So the variables would be y and z, h1, y, and z. Okay, and then here for our object here, we're going to have the bottom is g1, right? And g1, we're plugging in y values. g2, plugging in y values, right? You're plugging in y values and out are coming z values. Okay. Yeah, and maybe one other way that might make this easier is that if you're integrating with respect to x first, then you're going to get x equals and x equals. If you're integrating with respect to z second, then you're going to get z equals and z equals, right? So that might help you to figure out. And so that's one more possibility. There's three more, and it might not be a bad idea to go through and just try practicing, kind of sketching them and thinking through how those different surfaces would be oriented. Okay, so when you're actually going through and doing problems, how can you tell what the order of integration is? This is going to be fairly similar to how do you tell order of integration for double integrals. It's just kind of extended one more dimension. It's one more level more difficult. So, but first, before we get started in this, I want to be clear. This is, when you actually have to choose the order of integration, I'm going to start off by doing examples where you don't have to choose. But when you do get to the problems where you do need to choose the order of integration, there's kind of two factors to consider. One, the order of integration you want to integrate with respect to the things that you integrate with respect to, you want them to be one function, one piece, right? So you want, when you go through and think about the object, you want to think of the order of integration where you have the order where you'll have one piece, one function represents the entire part of the object. So to use the two-dimensional case, right? So if we think about it in terms of 2 dimensions, the idea is that we want a single function that represents the top and a single function that represents the bottom. So if you go through and you have something like this. So let's say in 2 dimensions, when you have something like this, if you go through and do an order of integration where you do top to bottom in this case, right? So if we're trying to do integration where we went this way, where we went top to bottom. So what ends up happening is that for the top to bottom, up to this point, the top comes from this function, comes from the parabola, and the bottom comes from the line. And then suddenly when you get to this point here, the top and bottom both come from the same function. They both come from the parabola. So that's going to make it a lot harder to go through and do integration if we go from top to bottom because of the fact that you have that split. So at minimum, you're going to have to go through and do 2 different integrals. And then the integrals, might be more complicated when you go to set them up. That's as opposed to if you went through and did set up your integral and you went from left to right, you could see that the entire left side comes from the parabola and the entire right side comes from the line. So you've got one single piece for the left and one single piece for the right. So when picking your order of integration in 3 dimensions, what we want to do is we want to think about how our surface is shaped. Does it have a single function that defines the top and a single function that defines the bottom? If so, then that is an option for a good order of integration to do top to bottom. Does it have a single front and a single back, a single function for the front and a single function for the back? Then front to back would be a possible order of integration. So what we want to do is we want to think about this case, what type of a shape, think about the shape that we have, and does it have a single function for top, bottom, left, right, so on. And then the second thing when it comes to determining your order of integration is to look at the variables of the functions that they give you. So in the problem, they're going to go through and they're going to give you information about the shape. They're going to give you, the shape is bounded by this or bounded by that. They're going to give information there. And if you go through and look at that information will give away typically what your order of integration should be, or at least, part of it, maybe the first stage of your order of integration. So I'll show you more specific examples, but look at the variables. In the surfaces. Those variables can help you. Like just to give you an example. So if you're doing a problem and they say, that your surface is bounded by z equals and z equals h2 of xy and h1 of xy. So they give you some information about the shape, and they say your shape is bounded by z equals something in terms of x and y, and z equals something else in terms of x and y. The fact that they gave you z equals suggests that z equals and then there's two variables suggests that you should integrate with respect to z first. So it's kind of a giveaway. Now that's as opposed to, let's say you're looking at a different problem, and in that problem they say your object is bounded by y equals something that's in terms of x and z, and something else in terms of x and z. You've got two different y bounds. Then this is saying, hey, you should integrate with respect to y first. So we'll do examples to make that clear. Okay, but again, those are giveaways, and where that comes from is it comes from the surfaces. It comes from the examples we've looked at. So if they're describing parts of the object to you, and those parts of the object, have one. So I didn't write it here, but this is z equals h2 of xy. This is z equals h1. This is here we've got y equals g1, g2 of x, and we've got y equals. If they give you parts of the surface, and those parts of the surface, the parts of the surface that have three variables in them have z by themselves, then that's this case. Okay, the things that have two variables, if they've got y and x, right, like this, that's going to suggest shape for the base. And the same thing here. We've got this is z equals and z equals. These are vertical surfaces, and so when you've got a surface and z is by itself, relative to x and y, then that's a surface that's usually above the x, and that's a surface that usually you want to integrate with respect to z first. And then in this case, if you had this example, you could see that if they're describing the surface to you and they've got the equations that have three variables in them, those have x by themselves, then that's suggesting that you should integrate with respect to x first. So that's one way. Those are two ways that you can go through and think about what should your order of integration be. Okay. And of course, to figure out this one, you often have to graph the function. A big believer in trying to graph the functions, when you're trying to figure out the order of integration. All right, so before we get into actually doing problems with the order of integration, let's just practice going through and doing some triple integrals. It's fairly straightforward. If you can do a double integral, usually you can do a triple integral. All right, so let's say they just gave us this triple integral and they said, go through and evaluate this. Okay, so similar to double integrals, what that tells us, you can figure out what the bounds are in terms of by looking at the order of integration. So the order of integration is going to be, first we have z, then x, then y. It goes inside out. And since z is first, that tells us that this bound is in terms of z. We go from z equals 0 to z equals x plus y. The second is in terms of x. So we've got x equals, and then the third is for y. And so we've got y equals and y equals. Okay, so to go through and integrate this 6xy with respect to z, when you're integrating with respect to a variable, you treat the other two variables as constants. So that means x and y are both constants. If x and y are both constants, then the antiderivative of a bunch of constants with respect to z is going to be those constants times z. So we're going to get 6xyz, 0 to x plus y. And then we still have y to 2y. And we still have 0 to 1. And we still have dx and dy. All right, and then take these are z bounds. So z equals, and just substitute them in for z. So we're going to get y to 2y. And we get 6xy times x plus y. And then minus with z equals 0 plugged in. If you plug in 0, you're going to get 0. So we don't have to put the minus 0. Okay, and now our next integral is with respect to x. The easiest way to do this is probably to go through and simplify it. All right, and then to integrate with respect to x, we treat y as a constant. So if y is a constant, we're just going to focus on this piece here. Antiderivative of x squared is going to be x cubed over 3. So we'll have 6y times x cubed over 3. And then here we're going to have 6y squared times x squared over 2, evaluated from y to 2y. And our dy is still in there. All right. And then we can go through and simplify this, right? So this is going to be, we're going to get 2 for that. Here we're going to get 3. So what have we got? We've got 2y x cubed. We're going to plug in 2y into that. So we're going to have 2y. Hold on, forgot our integral here. 0 to 1. We're going to have 2y and then 2y cubed. All right, and then we're going to have 3y squared and then 2y squared. And then minus, and then we plug in y here, we're going to have 2y times y cubed plus 3y squared times y squared. And then all of that is dy. All right, and then we can go through and clean that up before we finish. So what we got here, so that's going to be 8y cubed. So we have 16y to the 4th. And then we're going to have, what we got there, 4 times 3, so we're going to have 12 y to the 4th. And then minus 2y to the 4th plus 3y to the 4th. And then one more here, 0 to 1. We got what, 28 minus 5. So we're going to have 23y to the 4th dy. And so the antiderivative, that's going to be 23y to the 5th over 5, 0 to 1, and we get 23 fifths. Okay. So that's just an example of how to go through and do a triple integral. Let's try one more. Maybe a little bit harder. And then we'll get into problems where you've got to think at least a little bit maybe about choosing the order of integration. 0 to 1, 0 to 1, 0 to square root of 1 minus z squared. Then we have z over y plus 1 and dx, dz, dy. All right, so our order of integration, we're going to do x first, then z, then y. All right, so if we're going to integrate this with respect to x, we treat y and z both as constants. That means this thing itself is just going to be one big constant. And so the antiderivative is going to be that big constant times x. All right, and then we can go through and plug in 4x, and we're going to get z square root 1 minus z squared over y plus 1. All right, so just popping that in there. And if we plug in 0, we're going to get 0, so we just ignore that. dz dy. All right, and so now we're integrating with respect to z, and we've got z square root 1 minus z squared, so that's going to be a u substitution. So we do u equals 1 minus z squared, du equals negative 2z dz. So we need to have a negative 2z instead of just a z, so we can put in a negative 2, and offset that with a negative 1/2. And then we can do our substitution. So when you do the substitution, you got to change the bounds. So we're going to take 0 and plug it in. You get 1. Take 1, plug it in. You get 0. And then this is going to become square root of u. This becomes du over y plus 1 dy. And these bounds are now u bounds because we took our z bounds here. We popped them into our u equation here to translate them in from z to u. All right, and so now we can go through and integrate. So this is u to the 1/2. The antiderivative of u to the 1/2 is going to be 2/3 u to the 3/2. And then we've got 1 to 0 dy. And there should be a y plus 1 here in the bottom. All right, so we're going to have negative, take the 2/3, bring it out. So we're going to get negative 1/3, 0 to 1. And then you could pop in 0. When you pop in 0, you get 0, minus, and then you pop in 1 and you get 1. So we're going to have minus 1 over y plus 1 dy. You could pull that out, a negative out. So we're going to have 1/3, integral 0 to 1 dy over y plus 1. And then the antiderivative of this is natural log of y plus 1. 0 to 1. So that's 1/3 natural log, plug in 1, and you get 2 minus 1/3 natural log of 1. The natural log of 1 is 0, so we're just going to get 1/3 natural log 2. And that's the answer. Okay, so there's a couple examples of how to just go through and evaluate a triple integral. All right, so let's try some where you might have to, well, maybe the first couple here, you don't really have to do a lot of thinking to figure out the order of integration, but some of the later ones, we will. We'll work our way into harder and harder problems. Okay, so the first one, they give us, here's the triple integral over region E. They tell us we're adding up y. That's the temperature. That's the stuff. The function f that we're adding up is just the function y. And they tell us that E equals x, y, z evaluated where 0 less than or equal to x less than or equal to 3. We have 0 less than or equal to y less than or equal to x. And we have x minus y less than or equal to z less than or equal to x plus y. Okay. So now here's where what you want to do when you think about the order of integration is you want to think about the variables, that are being used, right, relative to, well, that's all variables, but relative to z. So if you look at the z variable, it is compared to things that have both x and y. So it's saying vertically we're between functions that have x and y. So if you go back, is that more like this or is it more like this? So what we said is we said that if you have z equals and z equals, or you're between, if z is compared to things that have x and y, then that usually implies that you want to integrate with respect to z first. If you have x related to y and z, then you'd want to do x first. Okay, and the same thing here. We integrated with respect to z first when we had z related to x and y. And so if we go to our problem, z is being compared to x and y. That's a giveaway that you want to do z first. And go through and do x minus y to x plus y. From the less than to the greater than. What you can do with these, which actually I recommend, and we'll get into more when we actually get into problems where we're choosing the order of integration, I recommend compartmentalizing them, similar to the way that I did when I actually went through and did the derivation. So you notice that when I did the derivation, I did the z all by itself, and then I just said, hey, you know what? Let's take our previous result for double integrals and just pop in a vertical strip into it, and that's how you get our triple integrals. So it's really, you could really think about it, it's like it's just two pieces. You've got this vertical strip, which you could even think of doing separately, and then after that, you do a double integral. And so you can go through and think about actually doing the problems. You can actually think about them that way by doing something like this, right? Where what I do is I go through and I define the innermost set of bounds and the first order of integration, first thing that we're going to integrate with respect to, and then I leave the rest unknown. We're still thinking it over. We're still trying to figure out how should I handle the base, but the top and bottom are done. All right, so that's something you could do. You don't really have to do it in this problem, but it's something that we will do on later problems. All right, so what about the remaining order of integration? Well, so the dead giveaway here is that the variable that just has constants on it usually is going to be the one that's last. Okay, so two variables innermost, one variable next, second, and then constants last. Now, sometimes you could have it where both of these are constants, and then it can become a more difficult choice. But in this case, we would want to go, that should be an x. We would want to just go 0 to x and integrate with respect to y next. And then the last one is the one that just has the constants. Okay. And then so, we can go through and just power through this again. I don't know whether I'll necessarily do every single problem, but just do a couple more. X minus y, x plus y. And so that's going to be 0 to 3, 0 to x. And then you could just pop those in. So x plus y minus y times x minus y. And then dy dx. And you could simplify this. This is xy plus y squared minus xy plus y squared and the xy's cancel. So we get 2y squared And then the antiderivative of this with respect to y is going to be 2/3 y cubed, 0 to x. And plug in x, you just get x cubed. Plug in 0, you get 0. So we're going to have 0 to 3, 2/3 x cubed dx. What is this? X to the 4th over 4. And so we're going to have 2 over 12. That's going to be 1 over 6. 1/6 x cubed, 0 to 3. And plug in 3, you get 27. 27/6. Hold on there. Yep, I made a mistake. This is why you have notes, right? The antiderivative, that's going to be x to the 4th. So we're going to have 1/6 x to the 4th, 0 to 3. Get 81/6, 27 halves. Okay. Let's try another. Again, we've got our region, x minus y, dv, y or E is enclosed by z equals x squared minus 1, z equals 1 minus x squared, y equals 0, y equals 2. Okay, so this is the first one where, I might think about going through and trying to graph the object. Do you have to graph the object? So you can try and get by without graphing the object. I know there are some people who do that. I prefer to graph them. I think it's a skill that you develop if you actually work at it, and you'll never develop it if you never try. Right? If you never work at it, you'll never get good at graphing the object. So it just kind of becomes a self-fulfilling thing if you never go through and even try sketching the objects. But I will say at a glance, just at a glance, without doing anything, the fact that I've got z equals and z equals suggests that my first order of integration is going to be with respect to z. Okay, so that's just something we've kind of talked about a couple times already. If you see a variable that's by itself, relative. Now, it would be a bigger giveaway if we had both of the other variables here. The fact that you only have x makes it maybe potentially that the order could be, could be different than that. But if this were z equals x squared, plus y, and z equals, y minus x squared or something, then it would be absolutely for sure. Then it's z first. But anyway, the variables that by themselves, that usually is a big hint. What does the object look like? If you go through and sketch it, it's not very difficult to sketch. So z equals 1 minus x squared. So that's a parabola opening downward, right? That's been shifted up 1. So you can just go through and go on your picture here. We've got a parabola opening downward. And it's a cylinder, right? So it extends. Whoops, did it wrong. Whoops. That's supposed to be on the XZ plane, not on the YZ plane. All right. Okay, and then since this is a cylinder, so you want to take that, you should extend it in the Y direction. And so we get all right. And then so that's 1 minus x squared, and then x squared minus 1, that is a parabola opening upward that's been shifted down 1. So it's going to start here. It's going to go up. it up. And pick a spot here and say goes up. Up. All right. And you can see that's what we end up getting, right? And if you kind of get practiced at, looking at the pictures here, we can see that the top is this curve here. The bottom is this curve here. So the top is all in one piece. We kind of talked about that. We want the top to be all in one piece when we're setting up our integral, and the bottom is all in one piece. So that's good for going through and integrating with respect to z first. So top and bottom are both one piece. That's as compared to just, this is good to just think about these things. What if you were going to integrate with respect to x first? So x first would be the idea of, you could think about it in terms of looking, thinking about the front and back. All right. So think about moving up the x-axis or moving in the x direction toward your object. Is the entire front one piece? Is the entire front one piece? Could we go through and integrate with respect to x first? Is the entire back one piece? Because that's what you do when x is first. So when z is first, it's top and bottom. When x is first, it's front and back. And when y is first, it's left and right. And so if you look at this, and again, you kind of just get used to working on these problems, that the front and back is not one piece. Part of the front comes from this curve here, comes from 1 minus x squared, and part of the front comes from this curve here, and part of the back comes from, again, it's kind of the same thing. Part of the back comes from 1 minus x squared, and part of the back comes from x squared minus 1. And so this is a good example where once we've got the picture, you would not want to integrate with respect to x first. However, what about y? Look at y. If we integrate with respect to y, we have one piece for the left and one piece for the right. So you could integrate with respect to y first here, and it would work just fine. It's a totally fine idea. However, by looking back at the way that they set up the problem, the fact that we've got z's by them, I guess y's are by themselves too here. Yeah, I guess the y's are by themselves. I guess that's kind of a giveaway that y is also an option. Anyway, the z's have more variables in them, so I think this gives it more of a hint that you should do z first. All right, so if you do that, so we're going to do z first, and again, I'm going to do the same thing I did before. I'm going to say, all right, I'm just not even going to think about the second integral. I'm just going to one at a time. So we're going to have z equals to z equals, and we're integrating with respect to z first, and we're just leaving the second alone, for later, to figure out later. All right, now so when we're doing from z equals to z equals, we want to go from the bottom to the top. So the bottom is given by x squared minus 1, and the top is given by 1 minus x squared. Okay. So once you've gone through and figured out that part, the next thing to do is to figure out the base. So the base of the object, the base is if you looked straight down the z-axis. The idea is the base is what you'd see if you looked straight down on the object. Or you could think about just taking the object and flattening it, and whatever you'd see would be the object, or the base, sorry. And so let's just kind of try and maybe sketch what that would look like. You can also try maybe drawing on this picture here. So the left, you want to think about in terms of left. So we're thinking in terms of x and y values. So x and y values are defined by left and right. Those are the y bounds. And front and back, those are the x bounds, that we can go through and put on our picture here. So what's the left? The leftmost part here is, if we talk about and just flattened this object, the leftmost part of the object is right here at y equals 0. The rightmost part of the object is right here at y equals 2. So on our picture down here that corresponds to that, you could go through and you could say, all right, well, this is y equals 0, and then here is y equals 2. All right, and then again, if we just took this object and flattened it, what would be the x bounds? All right, so the x bounds, the front, the part of the object that's the furthest in the x direction, that we can think of that as the front there. It's like really part of the front. But what is that? What is this? How can we figure that out? It's not given. It's not just right up there. The y equals 0 and y equals 2 are just given right in there. Well, to figure that out, this line here, this is where these two curves intersect. So to go through and figure that out, you could, to figure out where things intersect, you set them equal. And so you could do x squared minus 1 equals 1 minus x squared. And if you do that, you're going to get what? 2x squared equals 2, x squared equals 1, and then x equals plus or minus 1. All right, and that kind of tells us, right, that this is going to be x equals 1 and x equals negative 1. Okay, and that gets us our object. All right, so that's here and here. We get that square. Yep. Oh, it is a square. So yeah, from -1 to 1, 0 to 2, that's a square. And so this is the base. So figuring out the base is an important part of doing these problems. And so if you want to try and do all this stuff with the base without graphing the object in 3 dimensions, you can. There are people who do it that way, but I don't really do it that way. And I'm kind of determined that I'm not very good at explaining how to do it that way. All right. So now, once you've got the base here, what we need to do is we need to figure out what the dA is. And to do that, you just want to rely upon your experience from double integrals, because it's exactly the technique that you use from double integrals. So is this a type 1 or is it a type 2? Do you have a consistent top, a consistent bottom? One function to find the top, one function to the bottom, one function left, right? Those are the things to think about. So in this case, the top and bottom are both one piece, and the left and right are one piece. So it's both type 1 and type 2. When you can do both, I usually go ahead and do, kind of vertical. I think that students typically find that easier just because it's just the way that we orient, orient curves all the way from, kind of the first curve that you draw in intermediate algebra up until today is, you have curves that are functions, y equals a function of x. Those are curves that are oriented an x distance away from, or a y distance away from the x-axis. And so you can go, so that's what I would recommend is when you have the choice, do y and then x. So y, this is a y and then x, because you go a y distance away from the x-axis, and then you orient that along the x-axis to add up the area or volume or whatever problem you're working on. All right, so what would our y values be if we're going to do y first? Well, what does y do? Y goes from 0 to 2. And then last, x, and what does x do? X goes from -1 to 1. Okay, so I'm not going to go through and do this one just because it's kind of redundant. We've done a bunch of examples as how to evaluate a triple integral. What we could do, it'd be fun. This is not in my notes, so probably a bad idea, but we could go through and set up another order of integration where we do y first. Like, so let's say you looked at this and you saw the y equals and you said, oh, hey, I should do y first because I got the y equals. Let's do that. That's good practice. So we've got x minus y, and then we're going to do y first. We're going to leave this dA. We'll figure that out second. So if we're doing y first, you want to do, just like if you're doing z first, you want to do top and bottom. If you're doing y first, you want to do right and left. So the left here, left part of the object is at y equals 0, and the right part is at y equals 2. Okay, so that's the first order. And then if you're going to go through and do the second part, so that's the part where we've got to think about just like flattening the object, or what would you see if you just looked up the y-axis, if you just looked at it from this direction? Well, what you'd see is you'd see the two parabolas. right? And so the top one we have is 1 minus x squared. Bottom one is x squared minus 1, right? It looks like a circle the way that I drew it. It's not a circle, those are parabolas. All right, and so what we want to do is we want to go through and do from, again, if you have a choice, it's easiest to do from bottom to top. So the bottom is, in this case, so maybe it's a little confusing because it's you're doing different variables, but we're going, this is x and this is z, right? So this is the z axis here upward, that's this axis, and x axis. If you looked up the y axis, you'd see x versus z, z versus x. And so again, if you can, I think students are typically more comfortable going from top to bottom. And so that's going to be z next and then x last. And so that to get the equations for that, you have, if you're doing z, then you do z equals. And so we're going to go from the bottom one, which is x squared minus 1, the top one, which is 1 minus x squared. All right. And then finally, we have to figure out, oh, well, what would the x bounds be then? Well, if you're going to go from bottom to top, you need to figure out what would the sides be. So where are you going to start counting x? And where are you going to stop counting x? Well, we already figured that out, -1 to +1. And so that's the way to set up the second, a different order of integration. But if you evaluate both of these, you should get the same answer. Okay, so you could go through and you could do z first, or you could do y first. All right, and I did do this problem in my notes. Assuming you do it correctly, assuming I did it correctly, and you do it correctly, you should get -16/3. All right. Let's try another one. So we have triple integral of e x dv, and they tell us that e is bounded by paraboloids x equals 4y squared plus 4z squared and x equals 4. All right, so if you're going to go through and sketch this, which again, if you can, I think it's good practice. Well, actually, before we sketch it, what do you think the order of integration is going to be? Let's take a look. Based upon previous problems, what should we integrate with respect to first? Hopefully, you're thinking x, right? So if the variable that's by itself is the one that's relative to the other two is the one that usually is the giveaway. It's usually a giveaway that's the one you want to integrate with respect to first, and the other two form the base. All right, so if we were going to go through and sketch this, this is a, that's not a paraboloid. Not paraboloids. There we go. By the paraboloid and that. Okay, so anyway, the x equals 4y squared plus 4z squared. So that's a paraboloid. It's opening in the x direction. So it looks something like that. And then that. All right, and then we have, that's our paraboloid, and then x equals 4 is just a plane. So just pick a spot there. We'll say this is 4. It's just a plane that's going to hit our paraboloid, and it's going to hit our paraboloid in a circle. Just chops right through it, right at that point. And so this forms part of the shape. this forms the other part of the shape, and you get this object. So I don't think this is especially hard to go through and find this the shape here. If you struggle with something like this, then it might not be a bad idea to go back and watch the quadric surfaces video earlier in the semester. So that's that video. I went over how to go through and graph this in more detail. You know, but it is useful to be able to just kind of take a look at these and just recognize them. All right. Once we've got that, we can go through and set up our integral. All right, so let's do the first bound first. And so we're going to integrate with respect to x for, oh, I just kind of skipped a step here. So if we look at our surface, is the front one function? Is it one piece? Yes, this whole piece comes from x equals 4. Is the back one function? Is it one piece? Yes, it comes from this guy. And so front to back does work well here. All right, and now what is so this is the back is going to be the bottom bound. So the back is given by 4y squared plus 4z squared. And then the front is given by 4. And dA. And then the second set of integrals, we still have to figure out. Okay, so when it comes to the second set, you want to think about just taking the object and just flattening it, you know, or what you'd see if you looked up the x-axis. What would you see? You know, what does the shape look like? If you just smashed it flat, what would you see? Well, what you'd see is you just see this big circle. The question is, what's the radius of this circle? Right? We know that this point here is at, you know, this plane here that forms the front is at 4, and we know the back is given by this, but we don't know how, you know, what this distance is. How could we find that? Well, this circle here, this curve, is where these two things intersect. And when things intersect, if you want to go through and find how they intersect, you usually set them equal. So we can go through and do 4y squared plus 4z squared equals 4. And then you get y squared plus z squared equals 1. And that tells us the radius here is 1. Okay, so now that we know that if we took this and flattened it, we would get a circle and the radius would be 1. Now we can go through and set up the rest of the integral. Right? Now, one of the things that we talked about in our polar coordinates video is that when the base is a circle, you want to go through and use polar coordinates. So in this case, the base is a circle. So we want to use polar coordinates. So what you want to do here is you want to take dA and put r dr d theta for our polar coordinates. And then what we want to do is we want to do a substitution, right? So our polar coordinate adjustments, right? If you remember polar coordinates, we have, you know, x squared plus y squared equals r squared, you know, x equals r cosine theta, y equals r sine theta, and then, you know, tangent of y over x equals theta. Okay, if you look at these are oriented as if this curve is as if we had x and y, right? If we have x and y like that, then these work. However, do we have x and y? Is that what those are? Well, if we're looking up the x-axis or we're smashing this flat, what we've got is we've got z versus y, right? The z-axis is going to be this axis. If you looked up this, you'd see z going up and then y going to the right. Okay, so in that case, that means that we need to do some changes over here to our translation formulas. Okay, instead, this one where we had the x, we'll put a y. Where we had the y, we're going to put a z. You know, so then we're going to get y squared plus z squared. And then what is this guy? This is a y over x. So we're using z over y. Okay, and now take a look at, so can we use any of these to simplify? Well, when we are doing our translation, we have a y squared plus z squared. So this could be 4r squared instead of 4y squared plus 4z squared. And then we'll have x equals 4. And then our R bounds are R bounds. So recalling the way that our R bounds work, we want to go from the center most part of the circle to the outer edge. So from the center to the outer edge looks, look like that. So we want to go from R equals 0 to R equals, what's the outer edge? Oh, it's 1. And then we want to do that from theta equals 0 to theta equals 2 pi. And that gives us our integral. Okay, so from there, it's not especially difficult to go through and evaluate the integral, integrate with respect to x, right? You're going to get x squared over 2, plug in 4r squared, then multiply that result by r, then integrate with respect to r, and so on. Assuming I did not make any mistakes and you do not make any mistakes, when you get to the answer, it should be 64/5 pi. All right. Next example. So one of the things that you can do with triple integrals is you can use them to find volumes. So I think we went over this with double integrals, how you can use double integrals to find areas. You can use triple integrals to find volume. Okay, so let's just kind of really quick recall triple integral, we're adding up f of x, y, z over a volume that's defined by some region. Okay, well, if you went through and instead of adding up temperature at every point, right, instead of going at every point and saying, okay, this temperature here is 75 degrees, so we're going to add up all these 75 degrees. If at every point, instead of the value being 75, if it were just 1, right, if we kind of just go back all the way to the beginning, this cube, if we took the cube here and we just put a 1 here, right, then the amount of f of x, y, z inside of the box would have been 1 times change in x, change in y, change in z, which if it was just 1 times change in x, change in y, change in z, then you just end up with just change in x, change in y, change in z. You just end up with a volume. Okay, so what you can do to go through and take our setup here and make it so that instead of adding up f of x, y, z, we end up adding up volume would be to just replace f of x, y, z with 1. And then you'll end up adding up volumes instead of adding up amounts of f of x, y, z. All right, so this is the amount of f of x, y, z in B. If we go through and do 1 dV, this is the volume inside B. All right, so let's try a couple more examples here. Find the volume of the solid enclosed by, this time it's paraboloids. Y equals x squared plus z squared, and y equals 8 minus x squared minus z squared. Okay, and so if you kind of just go off to the side here and sketch the object. So we've got paraboloids where we've got y by itself. And so the parabola y equals x squared plus z squared is going to be a paraboloid opening in the y direction. And then we've got 8 minus x squared minus y squared. That's going to be a paraboloid where you have 8 as your kind of starting value, and the negatives here tell us that it's opening in the negative y direction. So it's going to open this way. So you're going to get intercepts there and intercepts there. And so you get this outline here. So we've got a paraboloid on the left and a paraboloid on the right. All right, so we want to go through and set up our triple integral here. What should we integrate with respect to first? Well, as we've discussed, when you have a variable by itself, that variable usually is the one you want to integrate with respect to first. So we want to start with dy. Oh, and also we're finding volume, so we're just going to use 1 for f of x, y, z. And then we'll do dA. So we're going to figure out the second part of the integral, second. And so we'll do y equals and y equals. And so when you're doing y, the bottom bound is the left and the top bound is the right. So the left is x squared plus plus z squared, and then 8 minus x squared minus z squared. Okay. All right. And now the second part is going through and figuring out the base. To do the base, what you want to imagine is you want to just take this object and just smash it flat. Or think about what you'd see if you looked up the y-axis. What you'd see is the outermost part of the object is the circle here. That's what you're going to see. That's what's the most important. So how could we figure out what that circle is? Okay. Well, the way to figure it out is that if you want to figure that circle is the intercept between this paraboloid and that paraboloid, and to find intercepts of things, you set them equal. So we could do x squared plus z squared equals 8 minus x squared minus z squared. And then we're going to get 2x squared plus 2z squared equals 8, or x squared plus z squared equals 4. So we've got a circle, and the radius is 2. Okay. And so we can go through and translate this now. So when the base is a circle, you want to use polar coordinates. So we can translate this over to polar coordinates. The dA is going to be r dr d theta. We're going to go from y equals, and then instead of x squared plus z squared, we could do r squared and 8 minus r squared. And then for r, 0 to 2, and then for theta, 0 to 2 pi. And where did I get these translations from? It's kind of the same idea that we did on this previous problem here, where you've got z and y. And so I took the translation formulas and I adjusted them for a z and y axis instead of an x and y axis. So I did the same thing here. What do we have? We have a z and x axis. So I just took the normal x and y translation formulas and I translated them for x and z. And so that would mean that for x and z, we have x squared plus z squared equals r squared. So x squared plus z squared is r squared, and x squared plus z squared is r squared. Okay. And then you can go and you can do the rest of this guy. Assuming that you do it right and I do it right, you should get 16 pi. That's what I got. All right. Got a couple more here. Lots of examples. This is one of those topics that can be difficult. Triple integrals can be difficult for students. So lots of examples. Find the volume of the solid enclosed by x squared plus z squared equals 4. And the planes y equals -1 and y plus z equals 4. Okay, so this is the first one where they really don't give away what the order of integration should be. There is a hint here though. So the volume is enclosed by a circle. That suggests to me that the base is going to be a circle. Typically, if you've got a circle as part of the object, then usually that's going to end up being the base. Not always. There could be scenarios where you don't end up with the circle as the base, but typically, if you have a circle as part of your object, you're going to have a circular base. So you're going to get your chance to use polar coordinates. What I would do, I'd go ahead and I'd try and sketch this. This might be starting to get into problems that are a little bit harder to sketch. It might not be the easiest, but I'd go ahead and I'd try it anyway. So what do we got? We've got x squared plus z squared equals 4. So that's a circle of radius 2. And since there's no y, it extends in the y direction. It's a cylinder. All right. And let's go ahead and draw a copy of it over here. That's extending. All right, we've got our circle there. All right, what else? So that we got that circle, and then it's also enclosed by the planes y equals -1. Okay, so y equals -1. So that's a plane that's parallel to the xz plane. So it's going to cut through our object. This, you could kind of think about it cutting through, horizontally and vertically this way. And so that's going to be at -1. Let's call that -1. If we move it over here, it's going to end up on top of our circle. So it doesn't have to be the scale. Oh, that's actually not terribly far off. Anyway, let's say that's -1. So if you go up, you're going to hit the circle there, you can hit the cylinder there, you can hit there, you can hit there. And so this is one side of our object is at y equals -1. All right, so we've got this guy, this guy. So far you've got the sides, a region surrounding your object, and you've got a plane that's cutting it off at one end. So really we're just kind of, in terms of thinking about our shape, we're just looking for something that's going to cut it off at this end, and then we'll have an enclosed region. So that's what you want to think about. Is this going to cut it off at this other end? And so if we look at y plus z equals 4, what is that? That is also a plane. Okay, and it's a plane that is in the YZ plane, and that it extends in the x direction. Now, to go through and try and sketch it, what you can do is you can think about intercepts. That's a really useful way to going through and sketching these objects. So if you were to plug in y equals 0, so y equals 0 is right here. That's the z-axis. If you plugged in y equals 0, you get z equals 4. So the plane is going to strike the z-axis right up there at z equals 4. And if you plug in z equals 0, then you're going to get y equals 4. And so what it is it's a plane that's cutting through our object here at a 45-degree angle. So what you can do to go through and sketch this is you can could even maybe use a different color. You go through and just start drawing downward at a 45-degree angle. Boom, it's going to hit the top of our surface right there, and it's going to cut through until it gets to the far side, and then at that point that's the That's it. And then it continues on. All right. So I think this people don't have a hard time necessarily. Students don't have necessarily a hard time with this part. But the thing that kind of gets people is, what do you do now? Well, the fact that there's no x here means that you can take that line, that line that we just drew, and you can move it in the x direction. You can slide it in the x direction, cutting through our object. If you were to take that and slide it, right, this point here doesn't hit any more of the object because it's at the very top. So if you moved it this way, you're not going to touch the cylinder. Take this point here, it's not going to touch the cylinder. But if you took this point here in the middle, if you went through and just kind of slid it, it's going to hit the cylinder on the sides, right? It's going to hit it over here and over here. And so what you can do is you can go through and end up taking this piece here. I was doing so well. Of course, it erased part of the object. It's just going to cut through at an angle. So if you could imagine a can, right? Think about this like it's a can that's on its side, and then you've cut through at an angle. Okay, then this would be the top. It'd be this angular 45-degree top to the can, and then you got the bottom of the can. All right, and so here's cutting through directly, not at a 45-degree angle, right? This would be cutting through at a 90-degree angle. That's this is black circle. So the red circle is cutting through at a 45-degree angle instead of at a 90-degree angle. And so you get this different shape because of it. All right, and so what we've got here is this side is y equals -1, and this side is y plus z equals 4. And so we do have boundaries on our cylinder, that cut through it. All right, so now let's think about order of integration. Which order of integration do you think you should do first? So think about because if they didn't give it to us, they didn't give it away, right? With the way that they set up the problem, they didn't give us a bunch of y equals or z equals or x equals. But if you think about this object, if you think about doing top to bottom, what happens if you do top to bottom? You got two different pieces here for the top and the bottom. This is a piece here, and this is a piece here, top and bottom, the two pieces. Okay, so you'd have to go through and solve this guy for z, and you'd have a plus or minus root, a plus root for the top and a minus root for the bottom. What if we did front to back? Same thing. The circle, you'd have this is one piece, this is another piece. You'd have to go through and you'd have to cut it into two pieces. You'd have to have two pieces, a plus root and a minus root. You'd have two different parts there. And so the best scenario for having a single piece for each side of the object is going to be the y first, where you've got y equals -1. That's the left here, and then we've got y plus z equals 4. That's the right side. So you've got a left side and a right side that both are just one piece. And so that's the easiest. I would say that's the easiest order of integration to do here. And I did become accurate, and that is that the circle, if they give you a circle as part of the object, usually that's going to be the base. That's going to end up being the base when we go and we just take this object and just smash it flat. All right, so you could do y equals -z plus 4. If they'd given it to us this way, if they'd said, the planes are y equals -1 and y equals -z plus 4, that would have given away that the order of integration should be y first. But again, the point of these problems is to slowly kind of stretch your capabilities, so you could try and figure out what's the right order of integration to do. All right, so we're finding volume again, so we want to use 1, and then we're going to do y first, and then dA, and then R or D, it doesn't really matter what letter you use there. And then so our first guy here is going to be y equals to y equals, and we want to go, the bottom is the left and the top is the right. So the bottom is the left, so we're going to go from -1 to -z plus 4. All right, and that gives us our first integration. And then for our other two, we can go through and, well, actually, hold on. we're gonna end up with our circle, so we're gonna have to do some substituting. So we're gonna leave this dy, and so if you go ahead and take this and just smash it flat, what are you gonna get? All right, well, what you're going to get is you're going to get the circle. You're just going to get the circle that was given, the circle that's defining the cylinder. You're just going to get this circle, right? So you're just going to have z and y. And so that's, what's the radius of that circle? We can figure that out just by looking at this. It's 2. Okay, and then that looks like a z. That's supposed to be a 2. The z's have a line through them. Yeah, that's the difference. It's a 2 because it doesn't have a line through it. I think some people do 2s with lines through them. There, now it looks more like a 2. All right. What was I doing? Okay, yeah. So now we want to go through, and when you use polar coordinates, you need to translate. And so the translation, you need to translate the z here, right? So what we've done is we've gone through and we've replaced the x with a y and the y with a z. And so wait, didn't we already do this one with x and y? Yes, and so here's the translation formulas when we did this last time. And what we want to look at is, what is z? Z is r sine theta. And so we get r sine theta plus 4, right? So where the z is, you just want to pop in r sine theta. Plus 4 drops down, the negative is still there. And then here we're going to have r dr d theta. Okay, and then r goes from 0 to 2, and theta goes from 0 to pi. Okay. So in terms of the answer that you get from this, I think I did this one incorrectly. Actually, I'm looking at my notes here because I think I put r cosine theta there. I don't know that that makes a difference though, because even if you do that, I think you still get the same answer. So I think the answer should be 20 pi for that one. Even if you put r cosine theta there, I think it should still be 20 pi. Anyway, I'm sure if I got it wrong, people will let me know. Okay. Finishing up here, the last thing I wanted to look at are problems that are really good practice. Really good practice. They're in these in this section. So what it does is it goes through and it's and the instructions are to set up an integral 6 different ways. Okay. So the E is defined by y equals x squared, z equals 0, y plus 2z equals 4. Okay, I don't know if this one is particularly hard. It might be, but it's okay. Good to see hard examples as well as easy examples. So you want to set this up 6 different ways. So the 6 different ways we talked about, that's at the very beginning of the video, that there are six possible ways that you could do an integral. And so it's saying, show how to do this every possible way. Just like the others, I would start off by trying to sketch this. I think it's a lot harder if you can't sketch it, or if you don't have a sketch of it. So they tell you that y equals x squared is part of the object. So y equals x squared is a parabola. It's opening here to the right. And then you have z equals 0. That's the xy planes. That tells us we've got kind of a floor here to the object. And then y plus 2z equals 4 is a plane. And that's a plane where you have z equals 2. So if you just plug in y equals 0, that's the z axis. So when you're sketching this, we're sketching it on the YZ plane. So for the YZ plane, if you set Y equal to 0, then that's the Z axis. And so you're going to get 1, 2 units up to, if Y equals 0, you just kind of ignore this part, you get 2Z equals 4 or Z equals 2. And then if Z equals 0, so on the YZ plane, if Z equals 0, that's the Y axis, and then you're going to get Y equals 4. So we get, it's like this. And then again, no X. So similar to the earlier example, no X means if you took this and just extended it in the X direction, just slid it in the X direction, you'd end up getting a line like that. For that intersect, it would just slide along. You get the line up here too, but this is the one that we care about because it's going to intersect the parabola. Just kind of extend the parabola. It's going to hit here. It's going to hit here. And so this is the top, right? So this is kind of where some experience with these problems. So if this is the top, if this corner here, if this is part of the object, and this is part of the object, and this is part of the object, then there should be a curve that traces from here to here. And so that's going to be kind of that traces out the side of the top. So let's see if we can do that. Maybe it's easier if I start up at the top. Yep, way easier to do it that way for me with the writing tablet. Like that. And so that's what our object ends up looking like, is you've got the top that comes from this, the bottom, which is the Z underneath, and then Y equals X squared ends up, well, in this case, forming the base. But when we do it 6 different ways, we're going to have to find other ways to do it. All right. So, but first, we've kind of set it up and discussed it already using Z first. So let's do that. Let's do the order of integration with Z first. All right, so they want you to just leave f of x, y, z in there. Then we're going to do dz first, and we're going to leave this dA. We're going to leave that second part. All right, so if we're doing z first, then we need to have z equals to z equals. So what z things should we put? So the bottom, when you're doing z first, you want to go from top to bottom. So the bottom is at z equals 0, and then the top comes from this surface here. That is defined by our plane. And so to go through and use that, we want to solve for z. So you're going to get 2z equals negative y plus 4, and then z equals negative 1/2 y plus 2. So we're going to have negative 1/2 y plus 2. All right, and so that's halfway there. That's the first order of integration. And then to go through and split that into the 2 cases for the base, let's go ahead and just write what those would be. So we're going to have f of x, y, z, dz, and then here I'm just going to put dy dx, because that's one possible order of integration for the base. And then I'm going to put dx dy for the other possible. There should be 2 more integrals here. And then we're going to have 0 and negative 1/2 y plus 2, 0, negative 1/2 y plus 2. The question is, what are these outer bounds? All right, so to figure that out, you actually need to figure out what the base looks like. So if you took this object and just smashed it flat, what would you see? You're going to see the outline, right? So what's the outline of this object? It's the parabola and then this line. So what does that look like? So we got the parabola, the line. The line is at y equals 4, right? You can see that from here. All right, and so to go through and set up the integral, if you're doing x then y, so x then y, that's a type 2 base. If you watch the double integral video, that would be going through and doing it this way. I think that's not the easiest way to do it. Easier to go bottom to top because just people are more comfortable with that because they have more experience. But you could go through and do it from left to right. There's nothing against the rules there. If you do that, then the dx here tells us that we need to do x equals and x equals, and then the dy says y equals to y equals. And so what would the x bounds be for, the side for the parabola here? Well, the x bounds are going to be when you solve for x with the parabola. So go up to your parabola, which is y equals x squared. If you solve for x, you're going to get plus or minus the square root of y equals x. And so this is going to be negative root y to positive root y. And then what are the y bounds? They go from the bottom of the object in terms of y is at 0 and the top is at 4. Okay, and so that's how you do it right there. It's not any more difficult than that. If you've got dx, dy, just go through and solve for x in the curve, parts of the curve that define the sides, and then just look at the y to figure out what the bounds would be. All right, and now I think the easier way to go through and do it, if you've got, your curve is to go top to bottom. So if we do top to bottom, the top here is at, y equals 4. And the bottom is at y equals x squared. And so if dy is first, we do y equals, and then it goes bottom to top, so x squared to 4. And then what are the x bounds? X bounds are going to be here and here. To figure those out, you can go through and set, and this is where y equals 4 and y equals x squared intercept. You could set those equal. You'll get x squared equals 4. So you're going to get x equals -2 to x equals +2. All right, so that's 2 orders of integration. 2 out of 6. 2 out of 6 done. Okay, these are not the same. They're different. We've got dx, dy, dx. Those are different. All right, so we need to do 4 more. What should we do next? I think the hardest group is probably the last. It's probably x. X is probably the hardest. So let's save that one for last. Let's do y next. So if we're going to do y next, we're going to have our triple integral here, f of x, y, z. We're doing y next. Then we're going to do dA and d. So we need y equals and y equals. Okay, so let's look at our picture here. So we've got, so when it comes to doing, oh wait, no, I wanted to do, yeah. No, I wanted to do that, the one I'm doing, I want to do y last. Y is the hardest, sorry. Let's do x first. Sorry. I got confused there in terms of the order. So we want to do x next. So x is, think about what would you see of the object, or sorry, what's the front of the object? So if you kind of moved up the x-axis, what would you hit first? Okay, if you think about it, this piece right here, this curved surface, this is the side of the object. So you're going to hit that curved surface. And then if you keep going, you're going to hit that curved surface on the way out again as well, right? So you're going to hit that curved surface at the front, and you're going to hit that curved surface at the back. So that curved surface defines the front and the back. So where does that curved surface come from? If we go back and look at our things that we've got, is this part of the curved surface? No, that's the top. That's the bottom. So that's the curved surface. And so for when we're going actually setting up the integral, if you're doing front to back means you've got x equals and x equals. So what's going to define the front and back in terms of x? Well, it's going to be taking this equation and solving for x, which we've already done. So the front and back are going to be defined by plus or minus root y. So this is going to be, the back is negative root y, and the front is positive root y. So that's this piece here. This is root y. And then this back is negative root y. Right, and you can see where those come from. They come from this curve here just sliding upward because it's a cylinder. Okay, no z coordinate. And so if you slide that upward, right, you get this side here, including that point there. Okay, and then the back Slide this up. This makes up the back. All right, I think that's the hardest part, is recognizing the front from the back. Once you've done that, the next thing is to go through and set up the second order of integration there. So to split this into the second case. So when we do the second case, you're going to have f of x, y, z dx, and then we'll just do, we'll do dy dz for one of them. So we get negative root y to positive root y. And so this one is going to be y equals to y equals, and then z equals to z equals. And then for the other, we'll have negative root y to positive root y, f of x, y, z, dx, dz, dy. So we're going to have z equals to z equals and y equals to y equals. All right, so these outer bounds are going to come from the base. So what does the base look like if you took this object and just smashed it flat? So it can be a little difficult to see it. So you might want to spend a second to think about it, maybe hit pause on the video. You just took this object and smashed it flat in the x direction. So you're not smashing it flat downward. If you think about taking your hands and putting it in front and behind and then just smashing it flat, what are you going to get? Okay, so the answer is, are you ready? The answer is you're going to get this triangle. That triangle is going to be what you're going to see if you just took this object and flattened it front to back, or yeah, front to back. And so that triangle is what we want to integrate across. That triangle is defined by, the top is defined by this piece here. The bottom is z equals 0. And then this left side over here, right, is going to be y equals 0. All right. So when we're setting up our order here, so y equals to y equals. All right, so let's look at that triangle. We can redraw the triangle. It's okay. It's allowed. So let's just redraw the triangle over here. We've got the triangle, right? And then this side is y equals 0. This side is z equals 0. And this side is, what is it? It's y plus 2z equals 4. All right. And so if we're going to go through and do y equals to y equals, so y equals to y equals, that is a distance off of the, so y is a distance in this direction. That means you're going to have the triangle going to be going that way, like that. Okay. And so the left side there is going to be at y equals 0. And the right side there is going to be from the line. And to go through and get the equation, you can just take the equation and solve it for y. So you're going to get y equals negative 2z plus 4. And then you're going to do that from z equals what to z equals what? Well, from bottom to the top, right? So the bottom is at z equals 0. And the top is this point here. Did we ever figure out what that is? Right? I think we did. It's z equals 2, right? We figure out this was 2 units. So you're going to get 2 units. Okay. Now let's look at the same picture, but now we're going to orient the little rectangle the other way. So now we're going z first, and if you're doing z first is this direction, and so it's going to be a vertical rectangle. And so now we want to go from the bottom to the top. So bottom is at z equals 0. And then the top is going to be this, but solved for z. Didn't we already do that? Yes, negative 1/2 y plus 2. So we're going to get negative 1/2 y plus 2. And then finally, we've got what are the y bounds? So we're going to go from the left to the right. We're going to move that rectangle from left to right to cover this whole region. And so the left side is at y equals 0, and the right side is here, which is at y equals 4. We already figured that one out earlier. 4. Okay, so that one is a little bit harder, I think, than the orientation for z first. But then the real hard one is the last one. And so, I mean, that's what you're here for, is to learn stuff. So this one, I'm not going to claim that this one is easy. This one is the hard one. But let's go ahead and try that one. All right, so for the last one, we have f of x, y, z, and then dx first. Dx? No. Y first. Jeez. That didn't sound right. So we're going to have y equals to y equals. Then we'll leave this alone. All right. So y equals to y equals. Let's look at our picture here. So we've got, if you're thinking about the, what the y bounds are going to be, those are going to go from the left side of the object to the right side of the object. So from the left side of the object to the right side of the object. All right, so the left side we've already discussed. That's the parabola. So that comes from y equals x squared. And then the right side of the object is, comes from y plus 2z equals 4. And so if you solve that for y, you'll get, negative 2z plus 4. And so that part's not too bad. So we've got the left side is y equals x squared. And then the right side is negative 2z plus 4. Okay, almost there. Here's the problem. This part is hard. The next part is hard. At least I think it's hard. I don't know. You guys can tell me. All right, we'll do this one as dx dz. Oh, whoops. We shouldn't have a d there. We should have x equals to x equals, z equals to z equals. And then a second one here. And we'll do dz dx. And so we're going to have x squared to negative 2z plus 4. And then here we'll have z equals and x equals to x equals. Okay, so the question is, if you smash this flat, what do you see? I mean, smashing it flat this direction. So you take your hands and you just flatten it. What would you see? Hard to tell. This is what's hard. I think this is hard. Maybe it's not hard. You guys can tell me if you think it's hard. What would you see? Well, the answer to what you'd see is you'd see this curve. Let me use a different color. You'd see this curve here. This curve here is what is defining. Right? That's the curve you'd see. That's the outer edge. Right? And then the bottom, of course, you'd see this as well. You're seeing those two things. So you got the bottom, and then you see this piece here. This defines the outside of the object. That's the exterior that you'd see if you smash this flat. All right, well, what is this curve? This is a curve, so you could go through and you should be able, I mean, well, maybe not always, but sometimes with curves, you can go through and you can define the equation of them. Could we define the equation of that curve? The answer is yes. What that curve is it's the intersection of the parabola, right? The parabola that's here at the base that I'm tracing along, that's the parabola. It's the intersection of the parabola with the plane that defines the top. It's the intersection of the plane and the parabola. The intersection of the plane and the parabola. How do we go through and find the intersection of two things? Well, what you can do is you can set them equal, or in this case, you can substitute. Take y equals x squared and pop it into this equation. And what you'll get is you'll get x squared plus 2z equals 4. That right there is the equation for this curve. Okay. And so if you go through and you draw that, let me use a darker color. It makes me nervous that people won't be able to see it. X squared plus 2z, that's much easier to see, right? So what is that? That is a parabola, And going on our picture here, what parabola is that? It's this parabola. Like that. So I think that's pretty hard. I don't know, maybe not, you guys could tell me. But I think that parabola is a little bit hard to see there, but that's what that parabola is. And now that I've got it for you from here, the problem is really not hard. But getting that parabola out of the problem so you can do the base is fairly difficult. All right, once it's done though, the bounds here, you want to go from x to x. How do we go from x to x? Take this, x squared equals negative 2z plus 4. X equals plus or minus the square root of negative 2z plus 4. So we're going to go from the negative root to the positive root. Negative square root 2z plus 4. Positive square root 2z plus 4. And then you're going to do that over what z values? The z values are going to go from 0 to 2. We could redraw the picture. Let me go through and do that for you. I've drawn it in pink on here, but let's just we can just really quickly sketch it. We'll just sketch it right here. So it looks like this, where this is x squared plus 2z equals 4. Okay, and so what we just did is we went this way. How do I know it's that way? So I've kind of described it a couple times here. But if it's x equals, that's the distance in the x direction, right? So x equals, since this is the x-axis and this is the z-axis in this picture, right? So I'm just taking this and translating it over to here. If this picture here, then that means that this is the x-axis. If dx, the x direction is this direction, and so you're going to have, if you're doing dx, then it's going to go this way. All right, so that's how you can figure that out. So if it's dx, then it should go in, your rectangle, when you're doing the base, it should go in the x direction. And that's what we've got here. It goes in the x direction, and then you slide it up and down z. All right, so anyway, so if you take this and solve it for x, it'll give you the equation for the left side, which is going to be the negative root of negative 2z plus 4. And then the positive side is going to be the positive root for negative 2z plus 4. And then you want to move this rectangle from the bottom of the object at 0 to the top of the object at 2. And so that's the first one done. And then for the second one, we want to go z first. So if you're doing z first, that's going to be a vertical rectangle, right? Because the z direction is vertical. And so this is going to be the rectangle if you're doing dz first. And so we want to go from the bottom to the top. So the bottom is at z equals 0. And the top is comes from this curve here. But what you want to do is you want to go through and solve it for z, right? So what would that be? To do that, you want to move the x squared over and divide by 2. So we're going to get z equals negative x squared over 2 plus 2, right? Slide this over, you're going to get negative x squared, then divide by 2. So you're going to get negative x squared over 2. And then 4 over 2 is 2. And so that's going to be our bounds. We're going to go from the bottom, which is at z equals 0, to the top, which we just said was negative 1/2 x squared plus 2. Right? And then what would our x values be? So if you're doing that, if you're doing the rectangle from top to bottom, then you need to move that rectangle across the entire object. So you're going to start at the left side and stop at the right side. So what are those x values? Well, how could you figure it out? I don't know, have we figured them out yet? I don't think we figured them out anywhere yet. Anyway, well, the way you can figure them out is that it's where this curve, it's where, if you think of this curve, if that's this piece right here, it's where that curve has a z value of 0. That's the x-axis. If you just plug in 0 for this, you're going to end up getting 0 equals negative x squared over 2 plus 2. And that's going to have, the solution is going to be plus or minus 2 for that. So it's plus or minus 2. guess maybe an easier way to figure that. Maybe we did figure that out. No. -2 to 2. Maybe we didn't. Okay. All right. All right. All right. So I'll show you how to do that. Right. So we've got, this is our equation for the parabola. And what we want to know is we want to know what these values are, where the parabola hits the x-axis. The x-axis has a coordinate of z, has an equation of z equals 0. So you just take z equals 0 and plug that in. All right. So if we take -1/2 x squared plus 2, set it equal to 0, you get -1/2 x squared equals -2. X squared equals 4. And then x equals ±2. There you go. And that's the last one. So the last one's hard, but the previous two, I think, are totally doable. So hopefully you can follow. You could follow those. All right. That's it. That covers triple integrals. Thank you for watching, and I'll see you next time.